We present out paper, PartComposer, learning and composing part-level concepts from single image examples. We'll start with the problem and motivation. Our goal is to learn part-level concepts from single image examples, like these two chairs, and compose them into new objects. We focus on part-level concepts because they enable rich visual imagination, and we focus on single images since that's what most real or generated data provides, no 3D or multi-view input for objects. This task is challenging for two main reasons. First, part concepts are fine-grained and require structural understanding to compose into valid objects, unlike subject-level concepts. Second, we only get one image per part, so there's very limited supervision, making generalization to new combinations difficult. We build on diffusion model personalization. Most pipelines encode concepts using text prompts and learn token embeddings through fine-tuning, sometimes updating UNet or transformer weights. These approaches work well for subject-level concepts but struggle with parts, especially from only single-image examples. Some methods use cross-attention loss for disentanglement, but we find that alone doesn't effectively separate part-level concepts. A key issue in existing methods is that they mix or miss parts. For instance, break a scene often merges part identities when composing across images. In contrast, our method preserves the identity of each part in composition. Now, our method. The core challenge with single-image examples is poor data variability. For example, just two images yield only two known part combinations. So, we propose dynamic data synthesis to augment training data while preserving structure. In each training batch, we create a synthetic image by randomly pasting parts from input examples. This encourages exploring part combinations. We also generate an instance image by masking parts from one of the inputs. This helps preserve object structure. Both are created on the fly during training. Next, we address concept entanglement. Without explicit regulation, concept embeddings can leak or overlap information, causing the model to miss or confuse parts. To fix this, we propose maximize mutual information. We train a concept predictor on denoised latents to identify which parts are present. This predictor has two heads, a classification head to ensure the right combination of parts is captured, and a segmentation head to localize them. These losses guide the diffusion model to better disentangle and encode part-level information. Now we show our results. We first show comparisons of our method with several baselines. When learning and composing parts from this example, break a scene tends to mix and miss the identity of some parts, possibly due to its focus on subject-level concepts. Partcraft results in poor image quality, possibly due to its original design for large datasets. MoodAI struggles to compose meaningful structures with correct identity, possibly due to its capability in learning fewer than 6 concepts. We also compare our method with PIT, which trains priors for different object categories and directly does inference without fine-tuning. We first use their training data for this creature category and notice that their method alters or miss the identity of some parts, even with this in-distribution example, while our method preserve all identity. We also tested their product checkpoint on the chair example, and their method fails to generalize to this slightly out-of-distribution example. Our method do not assume any category constraint and can work across categories. Now we show qualitative results of our method. This is an example of the same category of images, virtual creatures, and 4 different compositions. When increasing the granularity of the part decomposition, our method also effectively learn all of the concepts. Our method also work on cross-category examples, for example, composing part S across a bed and a wheelchair. And this example across a wheelchair and gym equipment. Our method creates some wild imagination for examples like this lion and the truck. Our method is also flexible and scalable. We could effectively learn background concepts together with part-level concepts and naturally blend the composed objects into the background. Our method can also handle incomplete part combinations and generate complete objects with variations in the unspecified parts. Our method can also scale up to learn many single-image examples with a large amount of concepts at the same time, as shown in this 4-chair X maple. Thanks for watching.